Hi, I'm Miss Roger, and welcome back to Core Concepts in Algebra 2. Today's lesson is on rational functions graphs. Today's lesson is specifically tied to the Massachusetts Curriculum Frameworks for Mathematics. A-REI, Reasoning with Equations and Inequalities, number 11, and F-IF, Functions Interpreting Functions, number 5. Let's take a look at the lesson objectives. To determine the domain of a rational function, to find vertical asymptotes of a rational function, to find horizontal asymptotes of a rational function, to find slant asymptotes of a rational function, and to sketch the graph of a rational function using key features. Let's take a look at the definition of a rational function before we start some problems. A rational function can be written in the form f of x equals n of x over d of x, where n of x and d of x are both polynomials and d of x is not equal to 0. So we want to think about the domain of a rational function. And the domain of a rational function is all real numbers except x values that make the denominator equal to 0. So let's take a look at two examples. What is the domain of f of x and g of x? So if I look at f of x, I'm going to examine the domain. When is this equal 0? That's going to be our restriction. So I take my denominator, x minus 3, and I say, when is this going to equal 0? So my domain is going to be all reals except x can't equal 3. That's my domain. For this problem, I recognize a quadratic, so one of the first things that I want to do is factor this. So when I factor this, I'm going to think about this as x plus 2 and x minus 2. So I'm saying to myself, when is the domain, or when is the denominator, this can't equal 0. So what is this going to be? The domain is all reals except x can't equal negative 2 and x can't equal positive 2. Let's take a look at the vertical asymptotes. So the graph of a rational function has vertical asymptotes at the zeros of d of x. To find vertical asymptotes, find the zeros of the denominator specifically. So let's find the domain and the vertical asymptote of f of x for this problem. So again, I want to examine the denominator, and I want to see for what values can this not equal 0. So if I'm thinking about the domain first, the domain is going to be 1 plus 2x, where this can't equal 0. So if I subtract 1 from both sides and divide by 2, I'm going to get all reals except x can't equal negative a half. So this is my domain restriction. My vertical asymptote, which is often abbreviated as v period a, vertical asymptote, is going to be the equation x equals negative a half. This is where I'm going to have a vertical asymptote. And we're going to see what this means when we actually start to sketch this. Let's take a look at our horizontal asymptotes. So horizontal asymptotes can be determined by using the highest degree of n of x and d of x. So let f of x equal n of x over d of x, which is our definition of a rational function, and have n equal the degree of n of x and d equal the degree of d of x. So we have three cases here. We have case 1, case 2, and case 3. And we have an example that goes along with each. So if the degree of n of x equals the degree of d of x, what's going to happen? We're going to have the graph of f have a line of y equals a sub n over b sub m as a horizontal asymptote. So what does that mean exactly? If this is our example, f of x equals 3x squared all over x squared minus 1, what that's going to mean is our highest power is going to be the same. So here we both have an x squared. So that's going to mean that we take the coefficient that goes with each of these, and we're going to make this be y equals 3 over 1, which is just going to simplify to be y equals 3. So y equals 3 is our horizontal asymptote for this problem. And again, this is when the degree of n of x equals the degree of d of x. We're going to have a horizontal asymptote at y equals 3. 3. So our second case is when the degree of n of x is less than the degree of d of x. So what's that going to mean? We are going to have a horizontal asymptote at y equals 0. So if I take a look at my example, this has a highest power, a linear of 1, and this has a quadratic, x squared minus 16. So since my degree of the numerator is less than my degree of the denominator, my horizontal asymptote is going to be y equals 0. For my last case, my degree of my numerator is going to be greater than my degree of the denominator, and this is going to indicate no horizontal asymptotes. So if I look at my example, again, I'm focusing in on the highest degree. We have a cubic in the numerator and a linear binomial in the denominator. So 3 is going to be greater than 1, so we're going to have no horizontal asymptotes. If we want to start to extend this and think about all the possible asymptotes, we've listed out the horizontal ones. If we want to start to think about the vertical ones, we can also start to do that because we can have more than one asymptote. So for this problem, this is going to be my horizontal asymptote. If I want to think about my vertical asymptote, again, I want to think about the denominator and where my domain is going to have a restriction. So if I think about how to factor this, this is going to be x plus 1 and x minus 1. So those, x equals -1 and x equals +1, are my vertical asymptotes. And again, I would set each of these equal to 0 and solve. For this problem, let's take a look if we have any vertical asymptotes. So my vertical asymptotes, again, I'm going to factor the denominator to be x plus 4 and x minus 4. Set each of those equal to 0 and solve. And I'm going to get vertical asymptotes at x equals -4 and x equals +4. For the last problem, we did not have any horizontal asymptotes. But we are going to have a vertical asymptote. Again, I can set my denominator equal to 0 and solve. So my vertical asymptotes for the last example is going to be x equals -6. So we've seen vertical asymptotes, we've seen horizontal asymptotes, and there's one more asymptote that we want to keep in mind when we may have an example of this. Let's take a look at slant asymptotes. So when the degree of the numerator is exactly 1 more than the degree of the denominator, the graph of a function will have a slant, or what's called an oblique asymptote. So this case does not always happen, but when we have exactly 1 more, we need to consider this. So we're going to use polynomial long division to find the equation of the slant asymptote. So let's take a look at our example, and let's do polynomial long division. So if I set this up for myself, I'm going to think about x goes into x squared how many times? It goes in x times. And now I multiply it back. X times x is x squared. X times 1 is 1x. And now I subtract, and you want to be very careful when you subtract. X squared minus x squared is going to give me a 0. -1x minus 1x is going to give me -2x. I'm going to bring down my 0, and I added that in there. And again, I'm going to work this out. X goes into -2x, -2 times, and I multiply it back. -2 times x is -2x. -2 times 1 is -2. And I can subtract again, and I get a remainder of +2. So my slant asymptote is when I do polynomial long division and my answer without the remainder. So my slant asymptote is going to be y equals x minus 2. And the reason why I don't include the remainder is because as the remainder goes to increases or decreases, it's going to approach 0. So this right here is my slant asymptote. And again, I can confirm that the numerator, the highest degree is 1 more than the degree of the denominator. Let's take a look at the steps to graph a rational function. So the first step is to determine the y-intercept and plot that ordered pair. And the way that we're going to do that, remember, is by setting x equal to 0 for the function and determining what the y-intercept is. And we can do that for all functions. Our second step is solve for the x-intercepts and plot those ordered pairs. And again, remember, we can set the numerator equal to 0 and determine the x-intercepts. Our third step is to find and sketch vertical asymptotes. So we're going to set the denominator equal to 0 and realize that this is when we're going to have our vertical asymptotes. And these are always equations. Step 4, find and sketch horizontal asymptotes using the rules that we just discussed. And again, it's by determining the relationship between the highest degree of n of x and d of x. Step 5, determine if there are any slant asymptotes and sketch them on the graph. And again, remember, this is when your numerator is 1 more than the highest degree of the denominator. Step 6, plot at least 1 point between and 1 point beyond each x-intercept and vertical asymptote to get an idea of what your sketch is going to look like. And step 7, use smooth curves to complete the graph between and beyond the vertical asymptotes. So we're going to use these steps to now take a look at 2 problems. Let's take a look at our first problem where we start to put this all together. So f of x equals x plus 8 all over x squared plus 2x minus 8. So let's find all intercepts and asymptotes and then sketch the graph once we've done that. So our y-intercept. We want to find our y-intercept by finding f of 0. So when I find f of 0, this is going to mean that I substitute 0 in for all of the x values and solve. So I'm going to have 0 plus 8 all over 0 squared plus 2 times 0 minus 8, which is going to give me 8 over negative 8, which is negative 1. And again, I want to write this as an ordered pair, so my answer is going to be 0, negative 1. That's my y-intercept. So I'm going to plot that, 0, negative 1. My x-intercepts. This is when, again, I set my numerator equal to 0 and I solve for my x-intercepts. So I'm going to take x plus 8 and set it equal to 0 and get x equals negative 8. So negative 8 is one of the x-intercepts. And I'm going to plot that. Again, I want to write this as an ordered pair. So my answer, instead of writing x equals negative 8 because that's an equation, I want to make this more complete and say negative 8, 0 is the ordered pair that goes with that. My vertical asymptotes. This is when I examine the denominator and I want to factor it and see where I'm going to have vertical asymptotes. I'm going to set that equal to 0 and solve. So if I think about x squared plus 2x minus 8, when I factor this, and I'll factor it over here, x squared plus 2x minus 8. When I factor this, I'm going to get x and x, 4 and 2, and I'm going to have negative 2 and positive 4. So 4 minus 2 will give me 2. So this is how I would factor this quadratic. And again, I want to set this equal to 0. So I'm setting each of these factors equal to 0 in order to get my vertical asymptotes. So when I set each of these equal to 0, I'm going to have x equals positive 2 and x equals negative 4 as my vertical asymptotes. So I can start to graph those right now. X equals 2 and x equals negative 4. When I draw in asymptotes, I do want them to be dashed lines. This is x equals 2, and I'm going to have x equals -4 right here. So now I have my two asymptotes. My horizontal asymptotes, I'm going to look at the highest degree of the numerator and the highest degree of the denominator. So if you notice, my highest degree of my numerator is 1, and my highest degree of my denominator is 2. So if I think about this, and I think about my rules, n is less than d, 1 is less than 2, so what that's going to mean is I'm going to have a horizontal asymptote at y equals 0. And this is specifically my x-axis. If I think about slant asymptotes, I'm not going to have a slant asymptote. So this is none. And the reason that is, again, is because our highest degree of our numerator is not one more than the highest degree of the denominator. So since we have a horizontal asymptote of y equals 0, we're not going to have a slant asymptote. So now that we've set this up, we want to now start to think about what this sketch is going to look like. And when we're working with these, we do want to use our graphing calculators and get a better idea of what the points and whatnot are going to look like. So when we graph this and when we sketch this, we have to be mindful of the asymptotes. So as we think about what's happening, this is going to cross and approach our asymptotes here. We're going to have a sketch here, and those are going to approach. And we're going to have another one here. So you might be wondering how we built this. We built this using our graphing calculator, our table. We would make all kinds of ordered pairs and think about what's happening. And this is the type of thing that we're going to explore during class tomorrow. So what we want to get from this is our intercepts, our asymptotes, and be able to set this up. So then we can start to look at how to build the table, how to actually get these values. And let's see what the actual graphing calculator, what that's going to give us. This is a look at what the graphing calculator produces for the previous problem. So it is similar to our graph in our sketch, and we're going to take a look at why this works tomorrow and actually take a really hands-on approach. Let's take a look at another problem in which we find all the intercepts and asymptotes and then sketch the graph. So f of x equals x squared plus 3x plus 2 all over x minus 2. So our y-intercept, remember, is when we find f of 0. And this is like thinking f of x, and we're going to substitute 0 in for all of our x values. So 0 squared plus 3 times 0 plus 2 all over 0 minus 2, which is going to give us, in the numerator, 2 over -2, which is -1. And again, I want to write this as an ordered pair. And this ordered pair is going to be 0, -1. So I want to plot that point. That's my y-intercept. My x-intercept is going to be when I take the numerator and I set it equal to 0. And first things first, I need to actually factor this first. So I'm going to take x squared plus 3x plus 2, set it equal to 0, find its factors. And my x-intercepts are going to be when each of these equals 0. So I'm going to have -2, 0, and I'm going to have -1, 0. So those are going to be my x-intercepts. My vertical asymptote is when I take my denominator and see where this is going to equal 0. So I can take x minus 2, set this equal to 0, and x equals 2 is my vertical asymptote. So before we move on, I might as well plot my x-intercepts. -2, 0, and -1, 0. And maybe I even want to space this out a little bit more since it's a sketch. And my vertical asymptote is going to be x equals 2. X equals 2. For my horizontal asymptote, I want to think about the highest degree of the numerator and the highest degree of the denominator. So for this problem, my n is greater than d. Specifically, 2 is greater than 1. So what this is going to mean is that we have no horizontal asymptotes. For my slant asymptotes, in this case I am going to have one because the highest degree of my numerator is one more than my highest degree of my denominator. So I need to do polynomial long division. So I'm going to take x minus 2 and I'm going to see how many times x goes into x squared and work out this process. So when I do this, I'm going to have x goes into x squared x times x is x squared, x times -2 is -2x, and I'm going to subtract. 3x minus -2x is going to become 3x plus 2x, which is 5x. I'm going to bring the 2 down. X goes into 5x 5 times, and I'm going to again multiply it back. X times x is, 5 times x is 5x, 5 times -2 is -10, and I can keep going, but again, the remainder is not going to matter. So once I get to this point, I have my slant asymptote. My slant asymptote is going to be y equals x plus 5. And again, remember, the reason is because the remainder, as it increases or decreases without bound, it's getting infinitely close to 0. So x plus 5 is going to be my slant asymptote, and I do want to graph this. So this is a linear function, and I want to be careful with how I'm graphing this. So my y-intercept is 5, and again, this is a very rough sketch. We're going to look at it in more depth tomorrow with graph paper. So this is my y-intercept of y equals 1x plus 5, and I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, and down 1 over 1, down 1 over 1. I'm not really sure where this is going to be here, so I'm going to try and make it as accurate as possible without having a grid. And again, when I create a slant asymptote, I want to make sure I have a dashed line. So take the extra second and make sure your line is dashed. And now we're ready to sketch. So when we actually sketch this, we are going to see that we're going to have our function kind of cross our intercept up here. And if this were to keep going, I'd have a similar idea coming up here. And we're going to do this tomorrow with graph paper and our graphing calculators. But the key and most important part about this is getting our intercepts, our asymptotes, and being able to build that on a sketch. So when we come into class, we can build tables and really take a look at what this is going to look like together. When we sketch this problem on our graphing calculator, this is what it's going to look like. And tomorrow we're going to play with the window and take a look at specifically what this looks like and how our asymptotes are accounted for and our x-intercepts. So start to think about this tonight, and we're going to look at it more tomorrow. After watching today's video on graphing rational functions, let's look at the essential questions. What are the characteristics of a rational function's graph? What kinds of asymptotes are possible when graphing a rational function? And what causes discontinuities in a graph of a rational function? We're going to discuss what discontinuities means tomorrow. Think about these essential questions tonight. After watching today's video, try these. Find the domain intercepts in all the asymptotes of the following and then sketch the graphs. Thanks for joining me in Course Concepts to Algebra 2. See you next time.